So let's make a start on electron microscopy, and you guys can kind of look forward to giggling and laughing at me a couple of times at least in this tutorial, because for some reason I find the word microscopy, even that time for example, kind of really hard to get off my tongue. So it's a pretty common word, but it's something that I find difficult to say for some reason, so you can look forward to that. Now, we're talking here about the process of using a microscope, okay? So there's certain features of that, and we'll get to the electron microscopy. You see, we'll get to the electron microscopy in a moment, but for now, let's remind ourselves of what we're probably quite familiar with, which is what we would refer to as a light microscope. Okay, let's remind ourselves quickly of how that works, so that when we look at the electron microscope, we can sort of see distinguishing features and differences. All right, so let's do that. So let's remind ourselves that on here we have an eyepiece. Okay, and here's our eyepiece. Sometimes it's 1, sometimes it's 2, and this eyepiece has some kind of magnification, typically 2 times or 4 times magnification, that kind of figure. Okay, we also have this bit here, which we're going to refer to as the objective lens. Let me have said this bit, but I didn't show you which bit I meant. This part here, which is the objective lens. And of course, this lens is going to give an additional quantity of magnification. And the ones that you've got in school, a typical figure might be times 10, times 100 type options. Okay, so that's going to be pretty typical, and you're going to be used to those kind of things. Now, this little feature here, where we place the specimen, this is what we call the stage. Okay, so that would be good for you to have an awareness of. And what we place the specimen on, or we kind of literally slide in and place here, is the slide. Okay, so our specimen is going to sit on that glass or perspex slide and is going to sit there and be viewable by us. Now, let's start to think about focus. We have what we would call a coarse focus. Okay, that's like a rough focus. Like you get the approximate focus of the image with this knob here. And we have what we call a fine focus. A fine focus with this one here. So that's kind of like the final adjustments. Again, you guys are probably pretty used to this. And that leaves us with a really significant part, which is this area here, which of course emits light. Okay, and we refer to this part, we refer to this simply as the light. Okay, so that is what we're going to get with our kind of light microscope. I don't think there's going to be any particular surprise there, but we have a problem, and the problem is that there are numerous, and perhaps for really deep microscopic science, 2 significant weaknesses of light microscopes. So let's actually see what those weaknesses are. Light microscopes. Sometimes I think I should type this stuff in before I come on the videos, but I kind of like it that you guys are writing these things at the same time I'm writing them. My pace should be roughly your pace, right, I suppose. So what are some of the weaknesses of these microscopes? Well, first of all, they can only get to approximately 2,000 times resolution, or max resolution. Okay, now that sounds like a kind of a big number, but in a moment when we're talking about the electron microscopes, we're going to realize that millions of times of microscopy, of magnification, is absolutely possible and achievable, albeit in quite expensive conditions. But nevertheless, this resolution is not going to allow us to get down to something like to view what we'd be able to call things like organelles. Okay, so it rarely shows organelles. Okay, so think about things like a mitochondrion. Think about things such as those little tails on prokaryotic cells, the flagella. Think about, for example, ribosomes within eukaryotic cells. I mean, these are things that we're going to struggle to see, well, we're just not going to see with this type of light microscope. And look, the thing I'd say to you is that the school ones, the ones that you're probably used to using, you may have some different quality there, but it's going to be some kind of times 100ness. Okay, so times 100ness resolution. So we say max resolution about times 2,000. The ones you're using in school are probably a little bit less than that, depending on what you've got access to. So therefore, we've got certain limitations here. So where does that leave us then? What do we do in that context? Well, we want to see more details, and the world of science certainly wants to see more details. So we invest in these absolute bad boys over here, and we refer to them as electron microscopes. And of course, that is the title of this entire tutorial. So this obviously is where we're going to go with things. And I'm actually going to draw the internals of this for you in a moment, so just bear with me for that. But the first thing I want to do is I want to kind of give you, let me rewrite this over here. I kind of want to give you the big picture on what these things do, okay? Because obviously you can look at that picture. I mean, first of all, let's be hugely impressed at how beige someone has made an entire room. It's quite spectacular how dull you can make something look. But nevertheless, let's give some sort of big picture features of these electron microscopes. Well, first of all, I want you to realize there's two types. There's one's called a transmission type, more of which in a second. This is the type I'm going to draw for you in a moment, okay, transmission type. But we also have something called an electron scanning type, and I will tell you a couple of differences between them, okay? So one fundamental difference is that in the case of the transmission type, again, more of which in a second, we're actually passing light through a very, very thin sample and creating the image on a fluorescent reflection. Okay, so it's actually a reflection of the image itself. Okay, so that would be a distinction between them as an example. Now, we also want to realize that one of the massive advantages to these electron microscopes is that they have incredibly large resolutions. Okay, so we are literally talking about magnifying something millions of times. Okay, so on that basis, if I just take that a little bit further, it's hundreds of thousands of times magnification of light microscopes. So one nice thing for you to think about is that this fella here is potentially something like 100,000 times more powerful than this fella here, okay, and quite probably more actually. But nevertheless, we sort of see the real distinction of why this is such a powerful and important structure for us, particularly when we're looking at things like molecular biology. And actually, one of the things I should add to that before we go any further, I mean, depending on where you read this, it's going to get us down to something like a magnification of 0.1 nanometers. Now, it's hard to even comprehend how small that is. Just bear in mind that some textbooks might say to you 0.2 nanometers. We're talking about very, very small, tiny structures when we get to that level of magnification. Now, let's keep going. Because of this, they've been really important in the discovery of what we call microelements, okay? Microelements. In other words, the detail of what is inside things like cell structures. Examples, I've mentioned them already, but examples would be things like ribosomes, those protein synthesizing structures, more of which, of course, we talked about in other tutorials, and even the details of something like the cell membrane. Think about that notion of that sort of semi-permeable or partially permeable membrane. To be able to look at that in detail, we have to go down to very, very tiny structures and be able to look at them clearly. Now, one of the things you might find interesting is that is actually that this electron microscopy happens inside a vacuum. So first of all, if we just consider this to be a big tube first of all, okay, inside that tube is a vacuum, okay? So it's important we realize that, because therefore the conditions required make this, first of all, very expensive, very exclusive, but also actually in some conditions quite hard to control. And it's actually a weakness of these microscopes is that they're darn sensitive. Okay, so they have to be dealt with in a very, very specific manner. Now, they're still very valuable to use. They provide unbelievable results, but nevertheless, we have to treat them very carefully. Now, they do produce 2D or 3D images. Okay, now the way I'd refer to you about that is that transmission type produce 2D images, two-dimensional images. Electron scanning type microscopes can actually produce 3D images of objects, which of course is very, very valuable. But on the downside, a lot to do with the fact that we have to use a lot of dyes and that the specimen has to be very, very thinly sliced, for example. We have no possibility of looking at living specimens. So one of the issues we have with these microscopes is that they can only look at samples which are effectively not living anymore. Okay, so partly because we have to thin them very thinly for the transmission type, partly because we have to add dyes to show up different features, and also because with the electron scanning type, we actually have to coat the specimen in metal. Okay, so obviously you can't do that with living cells. It's not going to work. So that's all well and good. I just want to, before we get into sort of the nature of magnification, I just want to show you very simply what we might find inside something like a transmission type electron microscope. Transmission type electron microscope. Okay, so let's see if we can just give you a big picture of this. We're not going to go into huge detail here. Well, my favorite bit is right at the start of our microscope. Picture this maybe up at the top of our microscope. We have this little object which I'm going to refer to now, and get ready for the coolest name ever, as an electron gun. Okay, an electron gun. Okay, so that's the fundamental here. Now, what the electron gun is actually going to do, not surprisingly, it's going to fire electrons, okay? And it's going to fire them like this. But where does it fire them? Well, it fires them to strike, actually, I suppose it's better described as be attracted to electromagnetic lenses. Let me just draw in a couple for you and just bring this down slightly. So this will all make sense in just a moment, don't worry. Just bear with me a second. Okay, so this electron gun effectively sends these electrons, and these electrons hit these electromagnetic lenses. Okay, so we get this kind of experience. Now, why is that relevant? Let me just type in the words electromagnetic lens, electromagnetic lens. Lenses, actually, because I'm going to point to more than one here. Now, you might just want to get a feeling for the fact that obviously electrons are negatively charged. So these electromagnetic lenses, effectively the electrons are being attracted into that area and then being reflected and diverted off by another one. But what happens here is we actually take our specimen, that was meant to be red, we actually take our specimen, and our specimen is here. Okay, our specimen is here. So those electrons pass through the specimen, and then way down here, they produce an image on what we call a fluorescent screen, and that is effectively how those electron microscopes actually function. Now, I repeat again, this is what we call the transmission type. In another tutorial on another course, we'll go into the specific differences of those kinds. But this is effectively how that image is created down here in the form of an image, electrons passing through our specimen, which has been dyed, cut very, very thinly, bouncing off electromagnetic lenses until it creates an image on a fluorescent screen. That is the big picture. Okay, now where that leaves me to want to talk to you is I want to finally talk to you about magnification. All right, and I want to give you an equation. And when you go to the questions on the EverLearner site, you're going to be practicing this in real detail. So I want you to know that magnification equals the size of the image. Okay, so bear in mind here, for example, whatever size our specimen is on this fluorescent image here, size of the image divided by, and I'm sure many of you could figure out what the next term is going to be, the size of the real object. Size of real object. Okay, so therefore we can start constructing examples of how we could actually calculate this, and many times in your exam you're going to need to do this, so it's something really worth putting time into. Okay, so I'm going to draw this little triangle here. Okay, so you guys will have seen these before. I'm going to sort of separate this triangle up in this way. So what we're looking for very often, is something like the notion of magnification. Okay, now that's our M from magnification up here. Well, we know that magnification equals what we would refer to as the image size, I'm just trying to keep the same colors, as the image size over the actual size. Okay, so if we want, or the real size, if we want to understand the magnification, we need to take our image size and divide it by the actual size. And we need a little, of course, little multiplication in there. If we want to understand or calculate the actual size of the image, we'd have to multiply the actual size by the magnification. So the point is that as long as we've got two of these three factors, we can calculate the other one. All right, so let me just give you a very basic example of that. Let's imagine that I have on my specimen, I'm seeing something. Maybe I've got some image here, okay, and on my image, I've got some onion cells. Okay, so let me just draw in a couple of onion cells like that. Perhaps they're like this, okay? And we know that those onion cells, because we've been given the calculation, we know that if we take this one here, on our image, on our magnified image, and we've got this distance here, we know, for example, that is 16 centimeters, just for argument's sake. And perhaps our question has told us that in reality, this cell here, which I'll kind of shade in kind of red here, we've been told in our question that this cell, its actual size is 0.3 millimeters. And the question we therefore want to ask is, what is the magnification to get it up to a size of 16 centimeters? So how would we go about doing that? Well, we would say, right, magnification equals, we know its image size, we know that is over actual size, okay? So we can now take magnification, and that's going to equal our image size, which for us is 16 centimeters, but we've got to make it millimeters. So let's make it 160 millimeters. We'll just put the units in for now, over the actual size, which is 0.3 millimeters. So if we calculate that, in fact, I don't think I've got my calculator open. Let me actually go in here. Let me actually get where is my calculator? Let me find it in here. Let me open the calculator. Come on, let's actually do this. So we want to take 160 and we want to divide it by 0.3, and that's going to give us a magnification of 533.3 times. Okay, so we've now got a situation where we can say our magnification is 533.3 times. A little X sign is good for magnification. Now, we will ask you lots more questions of those types when you take the quizzing on the website. But this is a process we really encourage you to get familiar with.